Hello students, today we are going to explain F black elements now. So F black elements means lanthanides and actinides. So in this video we are going to covering totally F black elements means lanthanides as well as actinides, and also some questions previously asked JEE examination questions. So today we are going to discuss F black elements. So in this video I am going to explain first lanthanides. After that we are going to discuss about the actinides. So in the first this is very familiar with your chemistry now. So this is periodic table. So in this periodic table is going to dividing 4 blacks. One is S black elements, and another is this is the S black element, this is the P black elements, and this is the D black elements, and this is the F black element. So in S black, even why these are called as S black elements, why these are called as P black elements, this is about D black, this is the F black elements. So in S black elements, the last electron in the last or outermost electron enter into the S black. That's why they are called as what? S black elements. In S black elements we have 2 groups. One is first year group and another is the second year group. In P black we have the third year, fourth year, fifth year, sixth year, seventh year, and this is the eighth year. This is the third year, fourth year, fifth year, sixth year, seventh year, eighth year. So you are very familiar with this periodic table. Now this is coming to the D black elements. This is the third B, fourth B, fifth B, sixth B, seventh B, eighth B, ninth B. This is eighth B. Iron, cobalt, nickel. These 3 rows are the eighth B, and this is the first B, and this is the second B. Now coming to our topic, it is the F black elements. So in F black elements we have these are also called as what now? Inner transition elements. So coming to D black elements are called as what now? Transition elements. Why these are transition elements? Their properties is transforming from S black and P black. In between the S and P black their properties are transforming. So transformation of properties from S black to P black via this D black. That's why they are called as what now? D black elements. Whereas in case of F black elements these are called as what now? Inner transition elements. Why these are inner transition elements? So generally these 2 rows are present in the inner of the D black elements. So this is 57. So actually 57, 58 to lutetium 71. So after the lanthanum, the elements are called as what? Lanthanides. Lanthanides elements starting from cerium 58 to lutetium 71, and actinides starting from thorium 90 to lawrencium 103. This is the thorium and this is the 103 lawrencium. So these elements are present in the inner of the D black elements. Actually D black elements are the transition elements, and these are called as these 2 rows specially placed in the bottom of the periodic table. They are called as inner transition elements. So why they are called as inner transition elements? So generally these 2 rows are present in the third B group. Third B group. This is the third B group. This third B group from 57, after the lanthanum 57, cerium 58 to lutetium 71, these are present in the third B group. These are present in the inner of the D black, inner of the transition elements. Therefore they are called as what now? Inner transition elements. So they are from 58 cerium to lutetium 71, and these are called as what? Lanthanides. The elements which follows the lanthanum are the elements after the lanthanum 57. They are called as lanthanides from cerium 58 to lutetium 71. This is the cerium and this is the lutetium 71. So cerium 58 to lutetium 71, there are totally 14 elements. They are called as what now? First transition series elements. So cerium 58 to lutetium 71, they are called as first inner transition series. And the second inner transition series is from thorium 90 to lawrencium 103. Thorium 90 to lawrencium 103. The elements after actinium. Actinium is the 89 and thorium is the 90. So from 90 to 103, there are totally 14 elements. They are present in the bottom of the periodic table in the second row, that is called as what na? Second inner transition series. Second inner transition series is from 90 thorium to lawrencium 103. First transition series is from cerium 58 to lutetium 71. So they are totally first inner transition series elements totally they are 14 and second inner transition elements are also they are 14. So totally 28 elements are present in the bottom of the periodic table under the inner transition series. And coming to, so this is the briefing of F-black elements. F-black elements are inner transition elements. So lanthanides 58 to 71 plus actinides 90 to 103. They are totally 28 elements collectively called as what na? F-black or inner transition series elements. And why they are called as 4F series elements and why they are also 5F series of elements. So lanthanides are called as what na? 4F series elements. Why they are called as in the lanthanides, the last are inner in the inner first series of elements, they are called as what not lanthanides. So in this the electrons are enter, the last electron enters into 4F series, but in case of actinides they are enter into 5F series of 5F orbitals. Therefore they are called as what not 4F series elements. They are called as 5F series of elements. Lanthanides are 4F, actinides are 5F series of elements. And why they are located separately at the bottom of the periodic table? Because of their properties, they are separately located at the bottom of the periodic table. So this is again we are going to discuss about the F-black elements. This is the two rows. They are called as what na? First inner transition series of elements. This is the second inner transition series of elements. So from cerium 58 to lutetium 71, this is the sixth period. This is called as what? The sixth period. This is the sixth period, and this is the seventh period. So from sixth period, this is the sixth period from cerium 58 to lutetium 71. This is the seventh period from thorium 90 to lawrencium 103. But they are both belonging to third B group. This is the third B group. So third B group of the D black. They are present in the inner of the third B, inner of the D black or inner of the transition elements. Therefore, they are called as inner transition elements from cerium 58 to lutetium 71 and 90 thorium to 103 lawrencium. And after this, so this is the position of the periodic table for F-black elements. They belong into group 3, and after the scandium, yttrium, lanthanum, actinium, these are placed in the periodic table belonging to third group, third B group. After scandium, yttrium, lanthanum, after scandium, yttrium, lanthanum, or after scandium, yttrium, lanthanum, actinium, they are placed in the periodic table. So placed separately to maintain structure. Placed separately to maintain structure, they are placed in the bottom of the periodic table now. And also they show similar chemical properties. That's why they are placed in the two separate rows. One is the 4F series and another is the 5F series. So that's why they show similar chemical properties. So lanthanides third group and sixth period, actinides third group and seventh period. So lanthanides group number is the third and lanthanides period number is the sixth. Whereas in case of actinides, third group actinides belong into third group, and actinides also belong into the seventh period. After this, coming to the electron configuration. So general electron configuration for the F black elements is N-2 F1 to 14, N-2 F1 to 14, and N-1 D0 to 1, and Ns2. So this is the general electron configuration of the F black elements. N-2 F1 to 14, N-1 D0 to 1, Ns2. So N-1, suppose if you take, this is the nucleus and this is the first shell of the, this is the N-2 shell. If you assume this as N-1, this is Ns. This is Ns, this is N-1D, this is Ns, and this is N-1D, and this is N-2F. So this is called as what now? This is ultimate shell, this is penultimate shell, this is anti-penultimate shell. In this case of F black elements, the last electron enters into this N-2F anti-penultimate shell. This is the penultimate shell, this is the ultimate shell, this is the penultimate shell, and this is the anti-penultimate shell. So the last electron in case of F black elements enters into this N-2 F1 to 14 only, not into N-1 D0 to 1 and Ns2. This is the ultimate shell, this is the penultimate shell, and this is the anti-penultimate shell. In case of F black elements, the last electron enters into this N-2 F1 to 14. That's why they are totally 14 elements. They are placed at the bottom of the periodic table. So lanthanides, in case of lanthanides, they are belonging to which group, which period? Sixth period. For n is equal to 6. If you place n is equal to 6, 6 minus 2f. 6 minus 2f means 4f. Therefore, in case of lanthanides, the last electron enters into 4f series, 4f orbitals. In case of actinides, the last electron enters into anti-penultimate shell, that is this 5f shell. So in actinides, electrons filled by 5f. In lanthanides, electrons are filled in 4f series, 4f orbitals. That's why lanthanides belonging to 4f, actinides belonging to 5f. So these are also called as 4f series of elements. These are also called as 5f series of elements. Actinides are 5f series of elements, whereas lanthanides are 4f series of elements, because their period number is 6, whereas in case of actinides, period number is 7. So 7 minus 2 means 5f. 7 minus 2 means 5f. 7 minus 1 means 6d0 to 1. 7, n is equal to 6. N is equal to 6 means 6s2. So that is the in case of lanthanides. In case of actinides, n is equal to 7. In case of lanthanides, n is equal to 6. So this is the electron configuration. So after this, so these are the elements belonging to lanthanide series. These are the elements belonging to lanthanide series. So for this, to remember one mnemonic, see, please never play some easy game to do homework every time you learn. So this is the mnemonic. From this mnemonic, we are going to remember all the 14 elements of lanthanides. So the first element in the lanthanides is the cerium. This is the praseodymium. This is the neodymium, promethium, samarium, europium, galladonium, terbium. This is the derbium. This is holmium, europium, thulium, ytterbium, lutetium. So there are 14 elements present in the lanthanides. So by using this mnemonic, we can remember easily. So cerium, Ce is the cerium. This is 58. This is 71. So 58 to 2. This is lutetium 71. So using this mnemonic, we can remember all the 14 lanthanide elements. C, please, never. C means cerium. Please means promethium, neodymium, praseodymium, samarium, europium, galladonium, terbium, derbium, holmium, europium, thulium, ytterbium, and lutetium. So these are the 14 elements. So these 14 elements can be easily, we can remember by using this mnemonic. See, please never play some easy game to do homework every time you learn. So this is the trick to remember lanthanide elements. So after this, so we are going to writing the electronic configurations.
Right.
So we are going to, so cerium is the, this is 58, 58, 59, this is 60, this is 61, this is 62, 63, this is 64, this is 65, 66, 67, 68, this is 69th element, this is the 71, and lutetium is the 71. So first, in order to write the electronic configurations, you take numbering. For example, this is the number 1. Suppose this is this is 1, this is 2, this is 3, this is 4, this is 5, this is 6.
White is amber.
How to idena? So this is 58, this is 59, this is 60, 61, 62, 63, 64, 65, 66, 67, 68. This is 69, this is 70, and this is the 71. This is the last 14th element. So first you have to write number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, this is 12, this is 13, this is the 14. Actually, what will be the general electron configuration of the lanthanide? So lanthanide's general electron configuration is the n-2f 1 to 14, n-1d 0 to 1, and ns2. So this is the general electron configuration of the lanthanides. But how can we write? So actually the electron configurations of lanthanides as well as actinides are in a irregular manner. So why they are in irregular manner? Because of a small energy gap between the inner shells or the small energy gap between the orbitals. Their electron configurations are not in a regular manner. Therefore, to write the electron configuration in correct way, you have to follow this trick. So from this trick, you don't take the 2 and 8 numbers. So 2 and 8 numbers. For example, this is the 2 number. So therefore, that is the 2 number, and this is the 8 number. So what is it is now? This is, don't take 2 and 8 numbers, or cross 2 and 8. Then write next number only. For example, this is the first. Actually, this is the first inner transition elements. It is because it is belonging to 6th period. Therefore, n is equal to 6. 6 means what now? 6 minus 2 means 4f. 4f 1 to 14. And this is 5d 0 to 1 and 6s2. This is the general electron configuration of the lanthanides. Therefore, for cerium you write what now? First, this is the 4f, this is the 5d, and this is the 6s. And for all these elements, the nearest noble gas, it is the xenon. So xenon, it is what now? What will be the electron? What will be the atomic number of xenon? Suppose helium is the 2, 8, 16, 2, 8, 18, 36, 54, 86. So this is the helium, this is neon, this is argon, this is krypton, this is xenon. So xenon is the nearest noble gas element to the all these first inner transition elements. Therefore, so the nearest it is what now, that is equal to 54 atomic number. So 54. So 54 it is the argon. So argon, after the argon, so one electron. This is the first element. Therefore you write what now, this is 1. And the second element is blacked. So don't take 2 and 8 numbers. Therefore you black this number now. So after the next number is what now, this is 3. So 2 is blacked. Don't take 2 and 8 numbers, or cross 2 and 8. Then write next number only. So after the blocking number 2 element, the next number is the 3. So after 3 we have the 4. This is the 5th. This is the 6th. Actually this is the off-field electron configuration. So galadionium is the off-field electron configuration which is more stable. Therefore it is always, it should be 7 only. And the last, this is the lutetium. This is the completely filled. Therefore what will be the 4f electrons now? 4f electrons having 14 elements, and 5d electrons and the 6s elements, 6s orbital electrons. So we are going to counting these 5d and 6s. So this is 7. After 6 we have again 7, and this is 7, but 8 is blocked. Therefore the next element is, the next number is the 9. Then this is 10, and this is 11, and this is 12, and this is 13, and this is again 14. And after that lutetium is again 14 only. And the electrons in the general electron configuration in the 6s, it is already, it is fixed. Therefore 6s always it should be 2 only. Therefore you write in 6s 2, 2, 2, 2, 2. So all having 6s 2 only. This is 2, this is also 2, and this is also 2. In 6s it is also 2, it is also 2, it is also 2. But what will be the atomic number of the cerium? 58. Already it is 54. Nearest noble gas is the 54. 54 plus 1, 55. 55 plus 2 in a 6s. 55, 6, 57. Therefore it will be 1 only. So in 5d we have 1 electron in case of cerium. 54, 55, 56, 57, 58. So this is the cerium. Next it is promethium. This is not promethium, this is the praseodymium. So 54 plus 3, 57, 58, 59. So therefore it should be 0. So in 5d we have 0 electrons in case of praseodymium. In case of cerium, in 5d 1, in 6s 2, in 4f 1 only. In neodymium, so 54 plus 4. So the nearest noble gas is the xenon. Xenon is the 54, and in neodymium 54 plus this 4, 58, 59, 60. Therefore it should be again 0. And this is the promethium, praseodymium. 54 plus 5, 59, 59, 60, 61. Therefore it should be again 0. In samarium, 54 plus 6, 60, 60 plus 2, 62. Therefore it should be again 0. 54 plus 7, 54 plus 7, that is 61, 61 plus 2, 63. Therefore again it is 0. And 54 plus 7, this is 61, 61 plus 2, 63. Therefore it will be 1. So this is different. And again 54 plus 9, 63, 63 plus 2, 65. Therefore again it is 0. And 54 plus 10, 64, 64 plus 2, 66. Therefore it is 0. And 54 plus 11, 65, 65 plus 2, 67. It is 0. And 54 plus 66, 66 plus 2, 68. Therefore again it is 0. But in case of thulium, what now? This is 54 is the nearest noble gas. 54 plus 13, 57, 67 plus 2, this is again 0. And 54 plus 14, 58, 68 plus 2, again it is 0. And 54 is the xenon, and 68 plus 2, 70, 70 plus 1. So therefore, this is the way to write electron configurations in easiest way. So again I will explain now. So these are the electron configurations of the lanthanide elements. Lanthanides usually it is belonging to 6th period and 3rd B group. 3rd group and 6th period. For 6th period n should be 6. 6 minus 2f. 6 minus 2f means 4f 1 to 14. 4f 1 to 14. 4f 1 to 14. 4f 1 to 14 and 5d. If you write n is equal to 6, 6 minus 1 means 5d 0 to 1. And n is equal to 6, again it will be 6s2. So this is the general electron configuration of the lanthanide elements. So lanthanide elements general electron configuration is 4f 1 to 14, 5d 0 to 1 and 6s2. So the important key point it is to write these electron configurations in a easiest way. You don't take 2 and 8 numbers. You don't take 2 and 8 numbers or cross 2 and 8. So this is the first element, second element, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th. This is the 12th one, this is the 13th one, this is the 14th one. So out of these 14 elements, first you cross the second element. This is the second element. And this is the 8th element. So you cross these two elements, second element and 8th element, or you don't take these two elements, second element and 8th element, and then you write the next number after the black number. You write the next number. For example, this is the first element. So for first element you write for 4f electrons 1. For second element it is black. Therefore you write the next element. The next number is the 3. 3, 4, 5, 6, 7. This is already it is half filled. Therefore, in the F black element there are 7 electrons. That's why it should be as usual 7 electrons. So don't change for gadolinium and don't change lutetium. So in lutetium 14 electrons in the F. 14 electrons in the F. So they are completely filled. Therefore this is extra stable. And in case of gadolinium there are 7 electrons in the 4F. So 4F 7 electrons it is incompletely filled or off filled. Off filled. Off filled is also extra stable. Therefore you don't change this gadolinium 7 electrons and lutetium 14 electrons. And remaining only for second element, 8 element you black. These two you don't take, second and 8th. And then you write the next number for the second and then write the next number for the 8. So the next number for the 8 is the 9. The next number for the second it is the 3rd. Therefore you write the first element 1 in case of 4F. The second it is black. Therefore you write the next number, that is the 3. 4, 5, 6, 7. This is as usually same because it is the off filled. It is extra stable. After the 7, 8 is black. Therefore you write the next number 9. Then after the 9, 10, 11, 12, 13, 14. This is the, again it is completely filled. That's why it should be 14 only. Now in case of electron configuration, 6s electrons are fixed. In every element, in case of lanthanide series, 6s orbital, it should have 2 electrons. Therefore, you write for 2 in case of 6s, 2, 2, 2, 2, 2, 2, 2 only. So this is also 2, 2, 2, 2 only now. Now, this is the nearest noble gas electron, the nearest noble gas elements for all these lanthanide series is what na? Xenon, that is equal to 54 atomic number. 54 it is an atomic number of xenon. 54 plus 4f1, 55, 56, 57, 58. Therefore, it should be 58 only now. So actually 54, this is the 54, it is the atomic number for the xenon. For example, if you write samarium now, samarium atomic number, it should be 62. Actually, it is the nearest noble gas, it is the 54. 54 plus 4f electrons are how much now in this case? 6. 54 plus 6. But we don't know the 5d. We don't know the 5d. Therefore, you can consider this as x. But 6s orbital also having 2. It should be equal to its it should be equal to its what now, atomic number 62. Therefore, x is equal to how much now from this? 54 plus 6, 60, 60 plus 2, 62. Therefore, x is equal to how much? X is equal to 0. Therefore, in this way, we can write the electron configurations in easiest way. Just you have to remember, don't take 2 and 8 numbers or cross the 2 and 8 numbers. So 2 is the praseodymium and 8 is the terbium. So these two atomic numbers 59 and 65. So you cross these two, second element and 8 elements. You cross these 2 and 8 elements and then write the next elements. After that you will get the electron configurations in this way. So this is the electron configurations of the lanthanides. In these electron configurations, the outer electron or the last electron enters into anti-penultimate shell, that is the n-2 f shell. So this is the important point now. So after this we are going to explain some elements of lanthanides. 14 elements, they are from lanthanum 2 to lutetium, and most of the lanthanum elements exhibiting the +3 oxidation state because it is the most stable oxidation state, and they are soft elements, they are soft metals and they are silvery white metals except samarium. So samarium is a steel hard like metal due to strong metal bond. So lanthanides are soft metals and they are silvery white metals except samarium. Samarium is a steel hard metal. Why samarium is a steel hard metal? Because in samarium we have the strong metal bonds. In between the samarium there are strong metallic bonds. That's why except samarium, remaining all lanthanide metals are soft and they are silvery white metals. Generally, hardness is directly proportional to atomic number. Suppose atomic number is increasing, hardness of the metal is also increasing. So therefore, hardness is directly proportional to atomic number. If atomic number increases, hardness of the metal is also increases. And these lanthanide elements generally exhibiting the lanthanide contraction. It is very important lanthanide contraction. So why it is useful in case of lanthanides and why lanthanide elements exhibiting the lanthanide contraction. Contraction means decreasing of size. So now let us discuss about the oxidation numbers. So lanthanides generally exhibiting these three common oxidation states. +2, +3, +4, these are the oxidation states of lanthanides. Is going to exhibiting +2 state, +3 state, +4 state. So how can you get this +2, +3, +4? By getting by the loss of 2 electrons, they will exhibiting +2. By getting the loss of 3 electrons, they getting +3 oxidation state. By getting the 4 electrons, they will exhibiting what now? +4 oxidation states. Out of these 3 oxidation states, common oxidation number, it is very important. This is the +3 oxidation state now. So +3 oxidation state is the common oxidation state. For example, if you take the, for example, cerium now. So cerium, so with the loss of 6s orbital 2 electrons and 5d orbital 1 electron, it will showing what now? +3 oxidation state. So like that, so the common oxidation number is the +3. by the loss of 3 electrons of lanthanide elements, they will exhibiting what? Plus 3 oxidation state. So ytterbium and europium and ytterbium, they will exhibiting the plus 2 oxidation state. So ytterbium is the plus 2 and ytterbium, europium is the plus 2 and ytterbium, this is YB, this is erbium, it is the plus 2 oxidation state. So they are exhibiting plus 2 because of stability factors. So lanthanum plus 3, this is the common oxidation state. So europium and ytterbium, they will exhibiting the plus 2 oxidation states. So plus 2 oxidation states may convert into, for example, you take the europium plus 2. So plus 2 may change into plus 3. So europium and ytterbium, they will exhibiting the plus 2 oxidation states. So europium plus 2 may change into europium plus 3. So this is increase in oxidation number, therefore it may be oxidation. So europium is undergoing oxidation, therefore itself acting as a reducing agent. This is the reducing agent. Therefore in plus 2 state, elements of lanthanides exhibiting the reducing agents, because plus 2 is changing into plus 3. Plus 2 is changing into plus 3. This is called as oxidation. Therefore itself acting as what? This is a reducing agent. Therefore in plus 2 oxidation states, lanthanide elements is going to performing reducing agents. And this is the common oxidation states. So in common oxidation states means lanthanide elements generally exhibiting the plus 3 oxidation state. All the lanthanide elements are going to losing 3 electrons. Therefore they will exhibiting the plus 3 oxidation state. Plus 3 oxidation state. And cerium, praseodymium, neodymium, terbium and dysprosium, they will forming what? MO2 type of oxides. MO2 type of oxides. So therefore in MO2 metal is exhibiting the plus 4 oxidation state. So metal is exhibiting plus 4 oxidation state. So in plus 4 oxidation state, for example, plus 3 is going to forming plus 4 or plus 4 is going to forming plus 3 now. So plus 4 is, this is the M. M plus 4 is going to forming as M plus 4. So M plus 4 is going to this is M plus 3. So M plus 4 due to M plus 3, this will be the decrease in oxidation number. That's why this is the reduction process. So the processes where reduction is occurring, they are called as what? Reduction reactions. So M plus 4 due to M plus 3. This is reduction. Therefore M plus 4 is acting as what? This is oxidizing agent. So M plus 4. Therefore cerium plus 4, PR plus 4, neodymium plus 4, terbium plus 4, terbium plus 4 is acting as oxidizing agents, because it involving what? M plus 4 due to M plus 3 type of reactions. M plus 4 due to M plus 3 is the reduction. Therefore M plus 4 is itself acting as what? Oxidizing agent. So this is what? This is europium plus 2, erbium plus 2 acting as reducing agents, and cerium plus 4, PR plus 4, neodymium plus 4, terbium plus 4, terbium plus 4 is acting as what? Oxidizing agents, because they are involving reductions, these are involving in oxidations. So the most common oxidation state is the plus 3. So plus 3 oxidation state is the most common oxidation state, and this is about the plus 2 oxidation state, and this is the plus 4 oxidation state. So generally these lanthanides is exhibiting plus 2, plus 3 and plus 4, but the most oxidation state is the plus 3 because of stability. And the next state is general properties of lanthanides. So lanthanides, in case of lanthanides, atomic radius decreases from left to right. This is due to lanthanide contraction. So in case of lanthanides, atomic radius from cerium 57 to cerium 58 to lutetium 71, with increase of atomic number, atomic radius decreases. Atomic radius decreases. This is called as what now? Lanthanide contraction. So what will be the reason for this lanthanide contraction? So actually from left to right, in the first inner transition series or in the second inner transition series, there will be a increase of effective nuclear charge with decrease of atomic radius. Why atomic radius decreasing? This is due to effective nuclear charge. Effective nuclear charge, it is increasing from left to right. So effective nuclear charge is nothing but Z by E. So with increase of effective nuclear charge, so nuclear charge is increasing from left to right. Therefore, nucleus attractions over the outer electrons is increasing. Therefore, atomic radius gradually it is decreasing. So why atomic radius decreases? This is due to lanthanide contraction. So what is this lanthanide contraction? So the inner reason it is effective nuclear charge due to lanthanide contraction. So effective nuclear charge generally from left to right, it is increasing due to lanthanide contraction. So effective nuclear charge means attraction of nucleus on the outer electron. It is increasing from left to right. That's why atomic radius decreasing. This is due to poor shielding effect of inner 4f electrons. So generally shielding or screening for f electrons is very less. So the shielding effect generally what now? Shielding effect. So shielding effect is more for s orbitals, less for p, and very less for d, and very less for f orbitals. So these in case of lanthanides, the inner orbitals are 4f orbitals. Their shielding is very less. The 4f orbitals having a very less shielding effect. Therefore, there will be a greater attraction of the nucleus on the outer shell. That will be increasing. Therefore, atomic radius decreasing. This is called as what now? Effective nuclear charge. It is due to lanthanide contraction. So therefore, atomic radius from lanthanum to lutetium 71 generally decreasing. From lanthanum plus 3 to lutetium plus 3. This is the atomic radii. Lanthanum plus 3 to lutetium plus 3 atomic radii gradually decreasing. This is due to effective nuclear charge due to lanthanide contraction. And also these lanthanide elements having high melting points, this is due to what? Packing of the crystal lattice. If it is greater will be the melting point. And also they will exhibiting conductance. They are good conductors of heat and electricity. And after this, this is about the lanthanide contraction. So this is the nucleus. These are the inner shells. This is suppose in case of lanthanide contraction, this is the N-2, this is N-1D, this is the NS. This NS shell is the ultimate shell. This is the N-1D. This is the penultimate shell. This is the N-2F. This is the anti-penultimate shell. So usually 4F. Lanthanide elements are belonging to 4F series. Therefore, N is equal to 6. Therefore, this will be the 4F. This is the 5D. This is the 6S. So usually 4F orbitals having a poor shielding effect. That's why they cannot shield the nucleus from the outer electrons. Therefore, this positively charged nucleus attract the outer electrons from the 6s. Therefore, atomic radius decreases. This is due to poor shielding effect of this N-2F anti-penultimate shell. So the last electron usually enters into this. This is the anti-penultimate shell, this is the penultimate shell, this is the ultimate shell. This is 6s, this is n-1d or 4, this is the 5d, this is the n-2f, this is the 4f. Usually this 4f orbital is having poor shielding effect. That's why this 4f series, this 4f orbitals never acting as a shield, never acting as a screen. Therefore, they cannot screen the outer electrons from the nucleus. Therefore, from left to right, what will happening now? From left to right, atomic radius decreases due to high effective nuclear charge. Left to right, effective nuclear charge gradually increases due to nuclear charge increases. Due to nuclear charge increasing on the nucleus, it will attract the outer electrons into itself. Therefore, it will be contracting. Therefore, it will also called as what now? Lanthanoid contraction. So, due to lanthanoid contraction from left to right, in case of lanthanoids, atomic radii gradually decreases. This is due to poor shielding effect of 4f orbitals. This is called as what? Lanthanoid, as well as it is actinoid contraction also. The same mechanism is also working in the actinides also. Therefore, it may also be called as what? Actinoid contraction. In case of actinides, it is actinoid contraction. In case of lanthanides, it will be lanthanoid contraction. So, this is about what? Lanthanoid contractions. So, what will be the lanthanoid contraction? Just now we completed. So, steady decrease in size with increasing of Z. Steady decrease in size with increasing of atomic number. This is the lanthanoid contraction. So, what will be the reason for this now? This is the poor shielding effect of 4f electrons. Poor shielding effect of 4f electrons. 4f electrons generally having a less shielding effect. And what will be the effect of this lanthanoid contraction? Generally, in case of D block elements, zirconium and hafnium, and niobium and tantalum. Similarity, there will be a similar properties between the zirconium and hafnium and niobium and tantalum. So 3d to 4d, in case of D block elements, what will happen? 3d to 4d usually in group. What will happen? From top to bottom in group, atomic radii generally increases. So here also from 3d to 4d usually increases, but 4d to 5d there will be a small change, there will be a small difference, negligible difference in the atomic radii from 4d to 5d. After the 4d to 5d, 3d to 4d usually in a group from top to bottom increases, but 4d to 5d there is no change, but 5d to 6d instead of increasing, atomic radii decreasing. Instead of increasing, atomic radii decreasing due to lanthanoid effects. So, by that lanthanoid contraction, there will be a similarity between the elements like zirconium, hafnium, niobium, tantalum. So, this is the consequence of the lanthanoid contraction. So, because of this similarity, we cannot separate the elements. We cannot separate the elements of same atomic radii. So that is the main consequence of the lanthanoid contraction. So this is the graph. So this is the atomic number on the y-axis and this is the atomic radii. So when a graph is plotted within the atomic radii on y-axis and atomic number on the x-axis, this is what will happen here from top to bottom. Usually this is the steady decrease in atomic radii. Steady decrease in the atomic radii from elements atomic number from 57 to 71. This is 57 and the last it is the 71. So 57 it is the lanthanum and 71 it is the lutetium 71. So this is on y-axis we are taking what now? This is atomic radii and on x-axis we are taking what? Atomic numbers. So this will showing what? This is the decrease. This is a steady decrease in atomic radii. Steady decrease in atomic radii. With increasing of atomic number, atomic radii gradually decreasing. This is happening. This is due to what? Lanthanoid contraction. So, So already this is already we discussed about the oxidation state. Stable oxidation state is the +3. Exceptions: cerium +4, terbium +4, europium +2, ytterbium +2. These are the +2 oxidation states. Terbium is the +4, cerium is also +4, and the most common oxidation state is the +3. And the variable oxidation, it is due to variable oxidation states, they will exhibit in the colors. So this is about the lanthanide colors. And after this, we are going to discuss about the chemical properties. So what are the chemical properties of lanthanides? So Ln means the element of the lanthanides. So when lanthanide elements is going to react with HCl, so what will happen? So Ln, so lanthanum when treated with HCl, lanthanide elements when reacts with HCl forming what now? Suppose if you, so generally this lanthanide elements is going to exhibiting the +3 common oxidation state. Therefore you can consider this as aluminium. So you consider aluminium plus HCl, AlCl3. Therefore LnCl3, this is the LnCl3 is the product. When lanthanide elements is going to react with HCl, so what will happen now? LnCl3 is forming now. So when lanthanide is going to react with halogen atoms like chlorine, bromine, iodine, etc. So you will getting again same LnX3. But here we are getting what now? Cl, hydrogen gas also. So lanthanum is going to react with 6 moles HCl. Lanthanide is going to react with 6 moles HCl. What will happen now? LnCl3. So 2 lanthanum, 2 LnCl3. This will be the 2H2, 3H2. So therefore, lanthanum is going to react with HCl or acids. They will forming what now? They will release the hydrogen gas. And lanthanum elements, they when they react with the halogen atoms, so you will getting what now? LnX3 type of halides. When react with water, so lanthanum is going to forming as a lanthanum hydroxide. LNO is taken thrice. LNO is taken thrice. Lanthanum when reacts with carbon upon heating, you will getting what now? LnC2 at 273 degrees Celsius. So at 273 degrees Celsius, lanthanum is going to, lanthanum elements when reacts with the carbon, you will getting what now? LnC2 is the compound. So when reacts with nitrogen upon heating, you will getting the lanthanum nitrides, LnN. So it will be, it seems to be ALN, because lanthanides is going to exhibiting Ln plus 3 is the most stable common oxidation state. So it is similar to what now? Aluminium. That's why you consider lanthanum elements what now? Al plus 3 type. Therefore aluminium when reacts with nitrogen, you will getting what now? ALN. So here also you will getting what now? LNN. So when reacts with sulfur followed by heating, you will getting what now? Ln2S3. Ln2S3. What is Ln2? How can we write this Ln2S3 now? So you assume Ln is what now? Aluminium. Aluminium plus oxygen or aluminium plus sulfur. Aluminium plus oxygen what now? Al2O3. Al means Ln. Ln2O3. So both oxygen and sulfur belonging to the same group. That's why Ln2S3, Ln2O3. So these are the some chemical properties shown by lanthanide elements. So lanthanum is going to react with the acids forming what now? Hydrogen gas. Lanthanum upon treatment with the chlorine or halogens giving what? LnX3, AlCl3 type. Lanthanum reacts with water, you will getting what now? AlO is taken thrice. AlO is taken thrice means LnO is taken thrice. Lanthanum when reacts with carbon at room temp at 273 degrees Celsius heating, you will getting what now? LnC2. Lanthanum upon treatment with nitrogen, you will getting the ALN type. LNN. Ln plus S. Lanthanides when treated with sulfur, you will getting what now? Al2O3, Al2S3 type. Ln2S3, Ln2O3. So these are the chemical properties of the lanthanides. So after this, so this is the chemical, these are the color and magnetism now. So many lanthanides are colored compounds. Why they are exhibiting the color? So this is due to what now? Many lanthanide ions are colored compounds. For example, lanthanum plus 3, lutetium plus 4 are colorless because of absence of the, what is the reason for this now? Lanthanum plus 3 and lutetium plus 4. Lanthanum. So what will be the lanthanum plus 3 now? Lanthanum plus 3. Already this is the lanthanum. So this is what now, in case of before cerium we have what now? 102. 102. 4F1. 5D0, 6S2. Lanthanum means 4F1, 4F1. So this is about, so lanthanum plus 3. Lanthanum plus 3. Actually lanthanum is what now? 4F1, 5D0, 6S2. So and before we have what now? Argon. This is xenon. So xenon is the 54, 54 plus 1, 55, 55 plus 2, 57. So lanthanum is the 57. So by the loss of three electrons, 2 from 6s, 1 from 4f. So you are getting the xenon electron configuration. So xenon electron configuration. So in xenon there are no unpaired electrons. That's why lanthanum plus 3 and lutetium plus 4 are colorless. So why they are colorless? Because of absence of unpaired electrons. For example, neodymium plus 3, this is exhibiting the purple color, and samarium plus 3 is the yellow color. So why they are exhibiting the colors? Because of presence of unpaired electrons. So in neodymium plus 3 and in case of samarium plus 3, we have the unpaired electrons. Therefore, they will exhibiting the colors. So unpaired F electrons are paramagnetic. If unpaired electrons are absent, they will be diamagnetic. If unpaired electrons are present, they are paramagnetic. So except F0 type, except F0, this means what now? This is F0 type. Except F0. In case of F0, we have what now? No unpaired electrons. Except F0 type. Lanthanum plus 3, cerium plus 4. These have what now? In lanthanum plus 3, cerium plus 4, there are no unpaired electrons. And F14 type. F14. So erbium plus 2, lutetium plus 3, they are paramagnetic because except F0 and except F14. So in F0, unpaired electrons are 0. In F14 also, unpaired electrons are 0. Therefore, they will not exhibiting the magnetic behavior. Whereas Yb plus 2, ytterbium plus 2, lutetium plus 3, they will have the unpaired electrons, therefore they are paramagnetic. They are paramagnetic. So after this, so this is the basicity now. So actually, in the first inner transition series, lanthanides, and also in case of second inner transition series, that is the actinides. They will exhibiting the basic property, basic hydroxides. They will exhibit basic hydroxides. So that basicity is decreasing from left to right. So why? For example, what will be the lanthanum plus 3 and lanthanum plus 3 to lutetium plus 3. So basicity generally decreasing. Basicity generally decreasing. Why basicity is decreasing? So suppose lanthanum is going to forming as LNOH taken rise, whereas lutetium is going to exhibiting the LuOH taken rise. But this is more basic, this is the less basic. LNOH taken rise is more basic, whereas LuOH taken rise is the less basic. So what will happen? Why they are less basic? So in a group in a row, from left to right, what will happen now? Size is decreasing. Left to right, what will happen now? Size is decreasing. So due to decrease in size, covalent character between the M and OH is decreasing. So what is there now in this? Metal and OH bond. Metal and OH. So from left to right, what will happen now? This is the metal and this is the OH. So from left to right, what will happen? Usually size of the metal is decreasing. Due to decreasing size of the metal, the covalent character between the metal and OH bond is decreasing, which reduces the basic character, which reduces the ability to release the OH group. That's why from Ln plus 3 to lutetium plus 3 or Ln OH second rise to lutetium OH second rise, basicity is decreasing. So once again I will repeat this now. So this is the important property now. So in most of the cases, in competitive examinations, this is asking now. So why basicity is decreasing from left to right? So what will happen from left to right? Usually due to lanthanide contraction, from lanthanum due to lutetium, atomic radii is gradually decreasing. So why atomic radii is gradually decreasing now? That is due to lanthanide contraction or due to poor shielding effect of the inner 4f orbitals. So here also from lanthanum due to lutetium, atomic radii is decreasing. So due to decrease in size, what will happen? The covalent character between the metal and OH bond is decreasing. So this is the metal and this is the OH. The covalent character between this metal and OH is decreasing. So due to decrease in covalent character between the metal and OH, which reduces the release of ability to release the OH group. So generally, what will be the basicity of the base, which will release OH group, which will release OH group easily? That will be the more basic. But due to decrease in covalent character between the metal and OH, this MOH is not able to release the OH group. Therefore, from lanthanum plus 3 to lutetium plus 3, basic character of the hydroxides decreases. So this is the important property of the lanthanides. So after this, these are the uses of the lanthanides. So neodymium and praseodymium, they are the strong magnets. They will acting as the magnets because of unpaired electrons usually. So eurobium and terbium, they are the TV phosphorus, and cerium oxide, they will acting as a catalyst in car exhaust. And this is the lanthanum and nickel, this is the alloy. This will acting as a hydrogen storage material. And the most important alloys of the lanthanum. So the alloys of the lanthanum, they are called as mish metals. Ln, lanthanum is the Ln. So alloys of the lanthanum are called as mish metals. So mish metals means 95% of the lanthanum and the 5% of the iron, and in some trace amounts of the carbon, sulfur, etc. elements. Carbon, sulfur and calcium elements. So what will be the important usage of this mish metals? So mish metal, it is nothing but it is the alloy of the lanthanides. So alloys of the lanthanum are called as mish metals. Mish metals combination, it is the composition. What is the composition of the mish metal? 95% of the lanthanum and 5% of the iron, and in some trace amounts of the calcium, sulfur, etc. elements. Sulfur also now. So what will be the purpose of this mish metals? So generally this using this mish metals we can manufacturing the bullets as well as in the defense materials, bullet proofs, as bullet proofs also. So using this mish metal, we can preparing bullets and bullet proofs materials as well as defense materials can be manufacturing by this mish metals. So these are the important uses of the actinides. So now we are going to discuss about the actinides. So actinides are generally from thorium to lawrencium. This is the second inner transition element series. Second inner transition series is consisting of atomic number from 90 thorium to 103 lawrencium. So 90 to 103, there are totally 14 elements. There are 14 elements from 90 thorium to lawrencium 103, and they are placed in the bottom of the periodic table separately, and this is also called as one inner transition element, and it is belonging to the third B group and also seventh period. So third group, again it is third group element, and seventh period element. These are belonging to seventh period and third group, and they will exhibiting the, in addition to plus 3 plus 4 plus 5 plus 6. So in lanthanides we have what now, plus 3 plus 4 plus 2 plus 3 plus 4. In addition to this, in case of actinides, they will exhibiting the plus 3 plus 4 plus 5 plus 6 oxidation states also. And in actinides, the last electron enters into the anti-penultimate shell of the 5F. Therefore, they are also called as what now, 5F series elements. 5F series elements. Why they are called as 5F series elements? Now, in this second inner transition series, the last electron or the outermost electron is entering into the anti-penultimate shell. That is the 5F orbital. That's why they are called as what now? 5F series elements. 5F series elements. So what are the general properties of these actinides? So most of the actinides are the radioactive elements. They are unstable. They containing unstable nuclei. They are radioactive elements. And actinide contraction, due to actinide contraction, here also the same thing is repeating from left to right in case of 5F series from thorium 90 to lawrencium 103, atomic radii decreasing. This is due to actinide contraction. So in case of lanthanides, that is lanthanide contraction, but it is in case of actinides, it is actinide contraction. So the same phenomenon is there in the 5F series elements. This is the second inner transition series element. So what is actinide contraction? So it is similar to lanthanides. The steady decrease in atomic radii due to poor shielding effect of inner 5F orbitals in case of actinides. So that is called as what? Actinide contraction. So from first element to last element, from first element to the 14th element, from 90 thorium to lawrencium 103, atomic radii gradually decreasing. This is due to actinide contraction. This is due to actinide contraction. And mostly the synthetic beyond uranium. So after the 92 uranium, after the element 92 uranium, the most of the elements are, they are synthetically, or they are man-made elements. They are man-made elements, therefore they are called as what? A synthetic element. Elements after 92 uranium are called as what? Transuranic elements. So again it is, these actinides are, most of the actinides are radioactive and they have unstable nuclei and actinide contraction. So here also we have one similar, which is similar to lanthanide contraction. So lanthanides, in lanthanides what now? Atomic radii from first element to the last element in the first series. First inner transition series also atomic radii gradually decreasing. Here also the same thing is repeating from 90 thorium to lawrencium 103. Here also atomic radii gradually decreasing due to inner 5F. In case of lanthanides, that is inner 4F. In case of actinides, it is inner 5F. That is due to poor shielding effect of the 5F orbitals. So that's why atomic radii is decreasing from thorium to lawrencium 103. So most of the actinide elements are synthetic elements. Most of the actinide elements are synthetic beyond uranium. So the elements after uranium are transuranic elements. Transuranic element, and all of they are radioactive elements. So these are some general properties of the questions. So this is about what electronic configurations of the actinides. So here also the main important trick. So these are the element first: actinium, thorium. This is Pa, uranium, neptunium, plutonium, americium, curium, berkelium, californium, etc., etc. They are 14 elements there now. But here, in order to remember, you don't take 6 and 8 numbers. So this is the first number. This is the second number, third number, fourth one, fifth one, sixth one, seventh, eighth, ninth, 10th, 11, 12, 13 and 14. So this is actinium is not now, this one. So you write from this one, thorium 1. This is 1, this is 2. This is 1, this is 2, this is 3, this is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the general electron configuration is n minus 2, 7 minus 2, 5f 1 to 14, 5f 1 to 14 and 6d 0 to 1 and 7s2. So anywhere it is the 7 because it is belonging to the 7th period. So now you write what now? Don't take 6 and 8 numbers now. So 6, this is the 6. Therefore you, what now this is, you black the 6 number and 8 number this one now. And this is the, what now this is, 7 is the off-field electron configuration which is more stable. You write as usually 7 only. So 14 is the completely filled, you write this is the 14. So this is in case of what now 5f. And after 5f we have what now 6d. And then is 7. So in 7 usually like lanthanides there are fixed numbers 2, 2, 2, 2, 2, 2, right, as it is 2, 2, 2 only. So in 7 as we have only 2 numbers. In case of 6d, but you write what now, first one it is 1 only now. In case of 5f, in case of thorium, what now, 1 number, this is 2. In 5f we have 1, in this, in case of this one 2 only, uranium is 3 only, this is 4 only, this is 5 only, but this is black now. So therefore, so 6 is black, therefore the next number is the 7. Again we have 7 is there, but after the 7 we have what now, this is black, therefore you write what now, 9. Then 10, this is 11, this is 12, this is 13, this is again 14. So therefore in case of 5F series, thorium 1, from this is 2, this is 3, this is 4, this is 5, this is black number, that's why you write the next number 7. After the 6 we have what now, 7 number. So this is curium, this is 7, this is 8 is black, therefore you write 9. So what will be the nearest noble gas now? This is radon. So radon is what now? Radon is the nearest noble gas. So 2, 8, 18, 36, 54, 86. So 86 is the atomic number of the radium. So 86 plus 1. 86 plus 1 is the 87. 87 plus 2, this is 89. But this is 1 because thorium is the 90. This is thorium is the 90. So in this way, we are going to write in the electron configurations in easiest way, and this is the only trick to write electron configurations in correct way. Okay, so this is the important trick. So students, if you have any doubt, you ask the questions on the scrolling on the
with the
screen.
help of your teachers.
Yes.
Yeah.
So ask the students now. Please ask.
ఇప్పుడు జరిగిన క్లాసులో విద్యార్థులకు ఎటువంటి సందేహాలు ఉన్నా దయచేసి మీ స్క్రీన్ పైన స్క్రోల్ అవుతున్న నంబర్కి కాల్ చేయగలరు. అదేవిధంగా టీచర్లు విద్యార్థులకి కాల్ చేయడంలో సహాయం చేయాలని కోరుకుంటున్నాం. If you have any doubts, students, you can ask them You can ask to the sir
regarding
by
the subject.
calling to the number which is scrolling on the screen regarding to the subject which have been taught you right now. All the teachers, please help the students to make the call so that students will get clarified about their doubts.
So please ask the questions, otherwise I shall close my class now. So thank you very much, students. I hope you understand well. Thank you very much.
ఇలా డౌట్ వస్తుంది కదా ఎట్లా